we need to solve for a moment m about the point A that will keep the system in equilibrium whenever an input force of 150 newtons is applied. And we know that whenever this input force is applied at the point D, the machine will apply another force at the point D, which I'll call F of D. And to solve this problem, we're also going to assume that this is the x-plane. So we're going to say that from point C to point D to x, this will act as our x-plane. So we'll start by saying that the sum of forces in the x direction is equal to 0. And to get the force F of D, we can say that F of D times the cosine of 60 minus 150 times the cosine of 30 is equal to 0. And solving this equation for F of D, we will get a force that is equal to 260 newtons. So we're now going to look at our free body diagram and solve for the unknown lengths A, B, C, and D, which will help us to solve for the required moment. So from the free body diagram, we can say that A is going to be equal to 100 minus 80 times the cosine of 30, and this will give us a length of 30.72 millimeters. For the length B, this will be equal to the length A divided by the tangent of 30 degrees. And this will give us a length of 53.21 millimeters. For our length C, this is going to be equal to 80 times the sine of 30 degrees. And this will give us a length of 40 millimeters. And for our length D, this is going to be equal to our length B minus our length C. And this will give us a value of 13.21 millimeters. So we now have all the information we need to calculate the required moment. So we can say that the sum of moments about the point A is equal to 0. And from the free body diagram and our calculated values, we can write the expression as 150 times 100 plus F of D times length B minus the required moment is equal to 0. So we can now plug in the known terms. So we'll have 150 times 100 plus 260 times 13.21 minus m is equal to 0. And solving this equation for m gives us the required moment that is equal to 18.43 Newton meters.